Hi, I'm Abhijit Sharma, and I'm going to present my work on evaluating autonomous vehicles against adversarial patches in real time using our Avatar framework. Till date, there have been a lot of work in showcasing the threat of adversarial patches in various applications, and these applications can be a simple classification task or it can be a real threat in surveillance cameras. So there have been a lot of demonstrations, but there is often an absence of the adversarial patch demonstration in autonomous vehicle scenarios, but we know that it is a serious threat in this application as well. Evaluation of our work is as follows. First, existing methods often apply adversarial patches to static image datasets, which lack real-world testing scenarios. Also, we found that the adversarial patches sometimes do not translate well to physical environments because there is a lack of photorealistic setting in the testing environment, and we need to involve real-world dynamics like changing lighting conditions, weather, or traffic scenarios. Hence, the patch efficacy must be evaluated in real time to reflect the real-world conditions accurately. Conclusion of our work are as follows. We first propose an avatar framework that introduces a real-time testing paradigm for evaluation of autonomous vehicles against adversarial patches. We also generate a Carla-based dataset to train our models as well as adversarial patches. We then integrate this trained adversarial patch into Carla so that we can test it in the simulation environment. And this framework is developed so that we can evaluate our adversarial patches in real time in Carla. We also provide a user-friendly GUI so that the user can set its test parameters and also configure the simulation as required. And then post-simulation, we also propose using an adversarial trace classifier to statistically predict the presence of adversarial patches in the scene. Patch testing, there is three-level stage and lot of existing work are in level 2 or level 3. But what we are proposing is using Avatar so that we can evaluate our patch in level 3 setting where the patch is online, the model is online, everything is inside the simulation environment, which accurately replicates the real world setting. So our pipeline of Avatar framework where the user has access to this user interface, GUI, where he can set the configuration file using the required test parameters. And with all the information that we have around the configuration setting, we also import the object detection model along with the adversarial patch that it want to be evaluated against. And then we send all this information into our Carla server, which then initiates and starts a simulation where we can visually see the adversarial patch in the environment. So in this slide, we show that how the GUI looks. So if you see, we are showing here a patch attack scenario where the user can set different patch conditions, and then it opens up a Carla window. In the test parameters, you can set the number of pedestrians you want, the number of vehicles you want, the type of weather condition you want. You can also choose your AI model as well as the patch that has been trained. When you start the simulation, it opens up this window where the simulation starts, and on the backend, it is the Carla that is running on Unreal Engine. This slide shows two test examples where on the left we have simulation without patch and on the right we have simulation with patch. As you can see here, the patch is applied on the vehicle and it's all inside the Carla simulation environment. And we test these adversarial patches against various weather conditions. And based on the user's test parameter and configuration setting, everything can be changed like the weather setting, the traffic, as well as the vehicle and also the patch. So there is a lot of parameters that can be changed and this is how the simulation looks. Second, we perform a real world testing as well so that we justify that whatever we have done in the simulation environment translates well to the real world as well. For example, here on the left, you can see we have a toy car experiment where we have printed the patch and then pasted over the car. And on the right, we have printed the patch as a poster and then applied on a real car. As you can see clearly that when the patch moves closer to the camera, it is able to evade the object detection. As you can see in both the pictures that all the cars which are even further away are easily detected, but the targeted object with the patch is not able to get detected. The aim is that we need to do some quantitative analysis so that the evaluation or analysis is not user dependent. What we do is that we record the confidence score of target object detection as a time series trace, and then we formally distinguish the trace of an original vehicle with that of an attacked vehicle. Figure represents the time series trace of confidence score of the target object detection vehicle over the course of duration. And you can see here that for an original vehicle without any adversarial patch, first, the confidence score is almost always high. Also, there is less variability in the confidence score over the course of simulation. As you can see here in this figure now, that after the vehicle has been attacked, the red traces, which is the adversarial patch on the vehicle, is first, the confidence score is very low, and second, there is a very high variability which reduces the reliability of the object detection algorithm. And hence, this showcases that there is a real threat that has been involved. And what we do next is use statistical measures to distinguish this between these two traces. We have a complete picture of adversarial trace classifier where first, what we do is we observe the behavior of original vehicle, and then we look at how different is an attacked vehicle from an original vehicle, and we perform some kind of mathematical formulations and then generate a kernel density estimation function, and then eventually we have a classification threshold based on the function that we have got. And as we can see in this figure, we have seen that when there is an original, like an unattacked vehicle in the simulation environment, the behavior is pretty like similar among each other. But when there is an adversarial vehicle, you can see how they are very different from a normal or nominal behavior. And this is how the adversarial trace classifier helps us to distinguish the two behaviors formally and statistically. Thank you. And if you have any more questions, feel free to contact me.